In this lesson, we will continue our discussion on particle motion or motion of particles. Now, we will first talk about uniform velocity, velocity that remains uniform, the rate at which the position changes remain constant. And then we will look at velocity against time graph. Then we will look at accelerated motion. And then we will develop a system of equations to deal with motion of particles. And finally, we will use those equations to solve problems. Alright, let's start by looking at uniform velocity, how the velocity against time is plotted and how it can be used. Here I have the picture of a particle that is moving with uniform velocity. Can you look at this picture and tell me what is its uniform velocity? If you look at this, I have represented the positions of the particle at intervals of 1 second. That means each second the position changes by how much? By 2 meters. Each second the position changes by 2 meters. It means the object has a uniform velocity. And I have prepared a table there for you. When time t equal to 0, the velocity is 2 meters per second. In other words, the velocity does not change. When the time is 1 second, the velocity is 2 meters per second. When the time is 2 seconds, the velocity is 2 meters per second. The velocity does not change. It means every second the position changes by 2 meters. The velocity is uniform and is equal to 2 meters per second. Now, this is a specific example. I'm going to use a general term. Let us now consider an object moving with a velocity, a uniform velocity of v meter per second. That means every second the position of the object changes by v meter. That velocity does not change. As time increases, the velocity remains a constant. Now, v remains a constant and does not change with time. How will a graph of v against t look like? Since the velocity does not change with time, a graph of velocity against time will be a horizontal line. Now, if I draw velocity on the vertical axis and time on the horizontal axis, that will be a straight line. What will this value represent? This value represents the uniform velocity v. If this v equal to 2 meters per second, then this will be 2 meters per second. But at the moment, we will not give it any specific value. We will call it v meter per second. Now, you know that displacement equal to uniform velocity multiplied by time. That does not need any explanation. Velocity is the rate at which the displacement occurs. Therefore, displacement will be uniform velocity multiplied by time. Now that is x equal to v times t. Is that right? If v equal to x over t, then x equal to v multiplied by t. Now look at the area under the curve. I have just shaded that area. Well, if I take it away, what does the area under the velocity graph represent? If you look at this, tell me, if I shade this area, this is the area shaded. The shaded part is a rectangle. What does the area of that rectangle represent? Now, what does this distance represent? This is a measure of the uniform velocity v. What is the length of the rectangle represent? The length represents the time t. That means if the length is t seconds and the width of the rectangle is v meter per second, what does v meter per second multiplied by t second represent? What is v multiplied by t? Let's do it in the next slide. V multiplied by t gives you the area of the velocity time graph. So if this is the velocity time graph, the area enclosed by the graph of v with the t axis, and that area is the length of the rectangle is t seconds and the width is v meter per second. Therefore, the area under that graph will be the width multiplied by the length. The width is v meter per second. The length is t second. What does that give you? That would be v times t. What is meter per second multiplied by second? That would be meter. So the area under the velocity graph, in other words, the area enclosed by the velocity graph with the x-axis is a measure of what? V multiplied by t is x, the displacement. So this is a measure of the displacement x. Now, this is very important for us. The area enclosed by the velocity graph with the time axis is a measure of the displacement of the moving object. Now tell me, is this true only if the velocity remains a constant? Not really. Now, if the velocity does not remain a constant, suppose I have a graph like this, velocity on the vertical axis, time on the horizontal axis, and suppose this is the velocity. Now, this is the velocity graph. In other words, the velocity increases, reaches a maximum, decreases, and so on. Now, in this case also, if you can measure the area enclosed by this graph with the t-axis, that will be a measure of the displacement. In other words, the area enclosed by the velocity graph with the time axis will be a measure of the displacement of the object. Very important concept. The area enclosed by the velocity graph with the time axis is a measure of the displacement of the moving object. So if I give you a velocity against time graph, and if I ask you to find the displacement of the object, what all you need to do is measure the area enclosed by the velocity graph with the time axis. All right. We will now talk about accelerated motion. Now tell me, what is acceleration? I'm sure most of you experience acceleration. When you put your foot down on the accelerator of your car, the speed of the car increases. So what is acceleration? What causes acceleration? Acceleration is caused by a change in velocity. If the velocity remains uniform, there is no acceleration. So acceleration is caused by a change in velocity. Well, acceleration is caused by a change in velocity. And we will represent acceleration by the lowercase a, and this a is caused. Now, how do you define acceleration? It is caused by a change in velocity. And we will define acceleration as the rate of change of velocity. Rate of change of velocity. What is the meaning of rate of change? Rate of change is change divided by that time. So how would you write an equation for acceleration? Acceleration equal to change in velocity divided by change in time. In other words, if the velocity changes from an initial value v1 to a final value v2, the change in velocity will be v2 minus v1, and this change happens in a time t2 minus t1. Then acceleration is v2 minus v1 divided by t2 minus t1, and we can write it like this. v2 minus v1, I can write it as delta v, and t2 minus t1 is delta t. So acceleration is delta v divided by delta t, the change in velocity divided by the time. Alright, can you tell me, what is the unit for measuring acceleration? Tell me, what is the unit for measuring change in velocity? Velocity is measured in meter per second. What is the unit for measuring change in velocity? Well, I know some of you are having trouble there. Well, if money is measured in dollars, what is the unit for measuring the change in the amount of money? Well, you went to the mall with $500 in your pocket and you came back with $20. What is the change in the amount of money in your pocket? It is $480. Is that right? So if the velocity is measured in meter per second, the change in velocity delta v also is measured in meter per second. And so what is the unit for acceleration? It will be meter per second divided by second. Is that right? That will be meter per second divided by second. What is that? What is meter per second divided by second? That will be meter per second squared. And we write it like this, meter per second squared. So acceleration is measured in meter per second squared. That is the unit of acceleration. Okay. Let's now look at the plot of velocity against time in this case. Can you talk about this? The initial velocity of the particle is v1 and the velocity increases steadily. What does that mean? It increases steadily. The increase is uniform. You can see a straight line until the velocity reaches v2. And if that happens in a time t, then v2 minus v1 over the time is the definition of acceleration. In other words, if you draw a graph of velocity against time, and if that graph is a straight line, then the slope of that graph is a measure of the uniform acceleration. You see, in this course, we will only use uniform acceleration. We will not look at particles moving with non-uniform acceleration. We will only look at uniform acceleration. That means velocity against time graph will be a straight line, and the slope of the graph will give you the acceleration. Now, this is a positive acceleration. How do you know if it is a positive acceleration? An acceleration is positive if the velocity keeps on increasing, right? So this is a positive acceleration. The slope of the velocity against time graph is the positive acceleration. Now look at the next graph. This is again a graph of velocity against time. What is the difference here? The particle starts with an initial velocity and its velocity decreases steadily until it reaches a very small value. The velocity is decreasing. Now, what kind of slope do you have for this graph? This time, the slope of the velocity against time graph is negative. It indicates that the velocity is decreasing. So, when an object picks up speed and keeps on increasing the velocity, the acceleration is positive. Whereas, if an object from a higher speed reduces its speed, the acceleration is negative. So, I will ask you, I think in one of the assignments I have asked you, write a paragraph about negative acceleration. So, what does negative acceleration mean? A negative acceleration in this context means the object is slowing down. In other words, the direction of acceleration is opposite to the direction of velocity. Now, I will also talk about a negative acceleration if the acceleration is in the downward direction. You see, we are used to understanding a downward direction as negative and an upward direction as positive. So, if this object is allowed to fall, it actually falls with an acceleration. Is that acceleration positive or negative? We will use it as negative, not because the speed of the object is reducing, but because the acceleration is directed in the negative y direction. You see that? So, we will use negative acceleration in those two senses. But most important to understand is that when the acceleration is directed opposite to velocity, when you brake your car, the velocity is directed forward and the acceleration is directed backward. The car is going to stop. That is a negative acceleration. Okay, let's do a small problem. A car starts from rest and accelerates uniformly for 5 seconds until its velocity reaches 10 meters per second. What is its acceleration? Well, that is a fundamental problem which can be done very easily by using the definition of acceleration. Now, a car starts from rest means that its velocity equal to 0 when you start counting your time. Or we say v equal to 0 when t equal to 0. And v equal to 10 meters per second at the end of time 5 seconds. Therefore, what is delta v, the change in velocity? The change in velocity is the final velocity minus the initial velocity. The velocity changed by 10 meters per second. Now, this change in velocity occurred in what time interval? Delta t equal to 5 minus 0, that is 5 seconds. What is the definition of acceleration? Acceleration is delta v divided by delta t. The change in velocity divided by the change in time. That will be 10 meters per second divided by 5 seconds. That will be 2 meters per second squared. It means every second the velocity of the object increases by 2 meters per second. That's the meaning there. Acceleration is positive. Velocity is increasing. That means when time t equal to 0, the velocity is 0. When t equal to 1 second, the velocity is 2 meters per second. When t equal to 2 seconds, the velocity is 4 meters per second. At the end of 3 seconds, the velocity is 6 meters per second. Every second the velocity increases by 2 meters per second. That is the meaning that the acceleration is 2 meters per second squared. Now the definitions of displacement x, velocity v and acceleration a can be summarized as follows. Well, in a simple language we can summarize these like this. Is that right? We have x equal to vt if the velocity is uniform, and v equal to at if the acceleration is uniform. But these are very simple relations. Alright. Uniformly accelerated motion means that the acceleration remains a constant throughout motion. As I told you earlier, we will only deal with uniform acceleration in this case. So we will now develop equations to describe uniformly accelerated motion. And to do that, we are going to use some notations. And let's put down some of these notations. When t equal to 0, we will assume that the object is at position x0. So x0 means the position of the object at t equal to 0. T equal to 0 is when we start our clock. So when we started the clock, where did you find the object? At x equal to x0. And what velocity did it have at that time? We will call that v0, v sub 0. So v0 is the velocity at t equal to 0, and the particle is at x equal to x0 at that time. Now very often I have a habit of representing the v0 as v sub I. Now if you see that, think that they are the same thing. What does v sub I stands for? Initial velocity. Initial, when you start your clock. Okay. It has a uniform acceleration a. In other words, the acceleration does not change. Its value is a at any given time t. So once again, we're going to look at a particle moving which is at the position x equal to x0 when t equal to 0, and at that time it has the velocity v0 and has a uniform acceleration a. After a time t, the position is x. X represents the position at any given time, and its velocity is v sub f, final velocity. You see that? As I told you, very often I will use v sub I for v0, initial velocity, final velocity. And I have also a habit. In place of v sub f, I will simply use v. V is the velocity at any given time, the final velocity. Alright, let's develop the first equation of motion. The first equation of motion is actually the definition of acceleration. Do you recall the definition of acceleration? Well, acceleration is change in velocity divided by time. So this is going to involve the final velocity Vf, the initial velocity V0, the acceleration and time. What all you need to do is write down that equation for acceleration. Can you write down that equation for acceleration? Well, I got that down for you. A equal to change in velocity, final velocity minus the initial velocity divided by time. Well, rearrange this. Multiply both sides by t. I can write A times t equal to Vf minus V0, or rearrange that and we get this beautiful equation. Vf equal to V0 plus At. Final velocity equal to initial velocity plus acceleration multiplied by time. This is the first equation. What is the first equation? Vf equal to V0 plus AT. Or I will simply sometimes say V equal to V0 plus AT. Look at the second equation. The second equation, we are going to use the concept we developed earlier. Suppose you have an object that starts with an initial velocity V0. So I'm going to use a graph of velocity against time to develop the second equation. Alright, now listen carefully here. You have a particle initially having a velocity V0 and it has a uniform acceleration and it has a final velocity Vf, and that happened during a time interval t. Alright, now consider an object which has an initial velocity V0 moving with uniform acceleration a for a time period t seconds and attains a velocity Vf during that time. Now dc is the velocity time graph of that particle, is that right? And what does the area under the graph represent? What does the area enclosed by the graph with the time axis represent? It represents the position function. It represents the displacement. The displacement x of the object during this time t is given by the area under that graph. In other words, if you can now measure the area of this shape, OACD, the area of this figure, OACD, is a measure of the displacement of the object. Can you tell me what that area is? Well, let's look at that area. This area can be divided into two parts. It is made up of this rectangle and this triangle. So in order to obtain the total area, I need only write down the equation for the area of the rectangle and then the equation for the area of this triangle. Add them together, I get the total area. And what does the total area represent? It represents the displacement of the object or the particle. Alright, area of the rectangle OABD is OA multiplied by AB. Tell me, what does OA represent in this diagram? It is the time t. You see that? OA is the time t, and what does AB represent? AB is the same as OD, and that is equal to V0. So this will be V0 times t. This is V0, that is AB, multiplied by OA is your time t. So area of this rectangle is V0 times t. What is the area of the triangle DBC? What is the area of that triangle? Area of a triangle is 1/2 base multiplied by height. 1/2 base, what is the base of the triangle? Is t. What is the height of the triangle? The height of the triangle is, if you look at this length is Vf, the final velocity, and this length is V0. Therefore, what is that length BC? That will be Vf minus V0. So the area of this triangle is 1/2 of base, that is t, multiplied by height, that is Vf minus V0. Okay. And that will be, look at the way I have modified it. Now, do you recognize I have used the red coloring here? This VF has been replaced by V0 plus AT. That is our first equation. VF equal to V0 plus AT. So the area of the triangle now is 1/2 T times V0 plus AT minus V0. Look at this. V0 and V0 will cancel. And that gives us 1/2 T multiplied by AT. And T multiplied makes it T squared. So that will be 1/2 AT squared. This is the area of that triangle. And the area of the rectangle is V0 multiplied by T. What is therefore the total area? The area of OACD is area of the rectangle plus the area of the triangle. What did we say the area of the rectangle is? V0 multiplied by T plus, what is the area of the triangle we just obtained? 1/2 AT squared. And again, look at another beautiful equation. X equal to V0T plus 1/2 AT squared. Well, this equation we got assuming that at t equal to 0, the particle is at the origin. If the particle at t equal to 0, if the particle is at some other position called x0, then you need to add that to this. If at t equal to 0, the object is at position x0, then the position function, the equation for x, the position or the displacement, can be written as x of t, x as a function of time, is x0 plus v0t plus 1/2 AT squared. And this is the second equation. The second equation is for the displacement of a moving particle, and in terms of the initial velocity, acceleration and time. And you see, very often x0 will be 0 because we can take the initial position to be the origin. But there are some cases where x0 will not be 0. So we will keep this form, although in most cases x0 will be 0. So how many equations do we have now? We have now two equations. What are they? Vf equal to V0 plus AT, the first equation. You notice that that equation does not contain displacement. The second equation, x of t equal to x0 plus V0t plus 1/2 AT squared. Now what is the quantity that is missing from this equation? This equation does not contain the final velocity. We eliminated the final velocity using the first equation. So you can see the first equation doesn't contain the displacement. The second equation doesn't contain the final velocity. Alright, we will now develop a third equation. Third equation of motion. What we're going to do is, we're going to take the first equation and manipulate it and produce a different equation. The first equation is Vf equal to V0 plus AT. I'm going to square both sides of this equation. Can you square both sides of this equation? Vf squared equal to V0 plus AT all squared. Now, I hope you know how to expand a square term like this. a plus b all squared is a squared plus 2ab plus b squared. Is that right? I think so. So how do you expand this? This will be square of v0, v0 squared plus 2 times v0 times 80, 2v0 80, plus the square of 80 is a squared t squared. Okay, now I'm going to factor out a 2a from these two terms. I think that will be a little difficult for you. Is that right? I don't know. I'm going to take these two terms and factor out a 2a. Now, you notice that there is a 2a here. There is an a there, but there is no 2 there. So how do I factor out a 2a from these two terms? Now, look what I'm going to do. I'm going to multiply that term by 2 and divide by 2. Does it make any difference? 2 divided by 2 is 1. Now what that did is, I can now factor out a 2a from there. So, when the 2a comes out, what is left in the first term? 2a has come out. What is left in the first term is v0t. And after this 2a, this is a squared. After 2a has come out, what is left here? There is a 1/2. You see that 2 in the denominator? This 2 has come out, leaving that 2 on the denominator. That will be a 1/2 a t squared. Now, how beautifully we produce that quantity. When 2a is factored out from these two terms, what is left there is v0t in here plus 1/2 a t squared in the next term. Okay. Now what has it achieved? Why did I do that? If you look at inside the parenthesis, what is this? v0t plus 1/2 a t squared. This is the displacement x. So we can now replace this by the displacement x. So we have the third equation. What is that? Vf squared equal to v0 squared plus 2ax. That is the third equation. I want you to write down these equations and learn them. The first equation is Vf equal to v0 plus at. That doesn't contain the displacement x. The second equation, x equal to x0 plus v0t plus 1/2 at squared. That equation does not contain the final velocity. And the third equation is Vf squared equal to v0 squared plus 2ax. Tell me, what is missing in this equation? It's very important to know that. There is no time here. You see, the quantities you must be looking at is initial velocity, v0, final velocity, vf, acceleration a, displacement x, and time t. There are 5 quantities. Each of these equations is missing one of them. Now, you should know that because when you want to solve a problem, which of these are you going to use? So this understanding is very important. Now, let's talk about acceleration of free fall. You see, all freely falling object, if I drop this ball, it falls to the ground. And as it keeps falling, it accelerates downward. All freely falling objects has a downward acceleration. Now, I told you some time ago that if you have a downward acceleration, we call it negative. Is that right? Now, what is the cause of this acceleration? the cause of this acceleration is the gravity. Earth is pulling it. And because of that, the speed will keep on increasing. And therefore, we say all objects fall with an acceleration called acceleration due to gravity. All falling objects have the same downward acceleration called the acceleration due to gravity, and we will represent that by the letter G. So, in place of A, when you want to deal with objects that are thrown up or down, that are subjected to this acceleration of gravity, we will replace our A by G. And this acceleration has been measured. What it says is that if I drop this object or this object or some other object, all these objects will actually fall with the same acceleration. All falling objects fall with the same acceleration, and that acceleration we call G, acceleration due to gravity. Its value has been measured as 9.8 meter per second squared. So any falling object has an acceleration of negative 9.8 meter per second squared. We use it negative because it is directed downward. Since the acceleration of a falling object is directed downward, we use negative G as the acceleration of free fall. Now, what is the acceleration of an object that is thrown vertically up? You see, the moment I throw this up, it begins to accelerate downward. That means whether an object is thrown up or simply dropped, both these objects have the same acceleration, the same downward acceleration, which is negative G. The moment the object is thrown up, it begins to fall freely with an acceleration negative G. There you are. You see, as the object is thrown up, the moment it is let go, it begins to fall back. And that is why it stops and then fall back. Its acceleration throughout the journey will be negative G. That's right. Its velocity while going up is positive, its acceleration is negative. So you must look at that. If when you throw an object up, while going up, its velocity is upward and its acceleration is downward because it is being pulled by the earth. So if the position of an object that is thrown up is y, the equations of motion. So because we are now dealing with vertical motion here, the position will no longer be called x, we will call it y. That means if you now want to construct equations for a freely falling object, we can use the same equations we developed earlier, but we will replace A there by negative G. So the first equation for a freely falling object is V sub F equal to V sub 0 minus GT, y equal to y0 plus v0t minus 1/2 gt squared. I hope you understand why I'm using y and not x. And what will be my third equation? Vf squared equal to v0 squared minus 2gy. Look at that, I forgot to change that a to g. It'll be minus 2gy. So these are the three equations for a freely falling object. What are the changes we made there? X has been replaced by y. and A has been replaced by negative g. Negative g is the acceleration of all falling objects. Okay, let's move on now. Let's do a small problem. An automobile moving with a velocity of 40 km/h along a straight road is braked uniformly to rest in 5 seconds. What is the average acceleration of the car during this time? Now, what are the information given to us here? An automobile moving with a velocity of 40 km/h. Now, first of all, you need to convert that km/h to meter per second. Do you remember the quickest way to do that? I have shown you in the first lesson. Km/h can be converted to meter per second by simply dividing by what number? 3.6. That's right. So this is your initial velocity when you start looking at it. When you start your clock, the automobile has a velocity of 40 km/h and it is braked uniformly to rest. What is the final velocity? It is brought to rest. The final velocity is 0. And this happened in a time 5 seconds. Let's write that down. V0, initial velocity, is 40 km/h. And that will be 40 divided by 3.6 meter per second. That is 11.1 meter per second. That is the initial velocity. What is Vf? Vf equal to 0. Alright, the time is 5 seconds. But all we need to do is to find the acceleration. We can either write down the equation for the acceleration right away or use the first equation. We can use the definition for acceleration. Acceleration is change in velocity, Vf minus V0 over time, and that will be 0 minus 11.1 meter per second divided by 5 seconds. That is negative 2.2 meter per second squared. Now, don't confuse the negative acceleration. I told you acceleration due to gravity is negative because it is directed downward. Now, this acceleration is negative not because it is directed downward. But why? Because this acceleration is directed opposite to the velocity. As the car is going forward, when you apply the brake, the acceleration will be backward. So the acceleration is negative indicates that the direction of acceleration is opposite to the direction of displacement. Another problem. The driver of a pickup truck going 100 km/h applies the brakes, giving the truck a uniform acceleration of negative 6.5 meter per second squared while it travels 20 meters. What is the velocity of the truck at the end of this distance? What is the time taken to travel this 20 meters? Always look at the problem and pick the data. What do we know? We know the initial velocity is 100 km/h. Convert that to meter per second, divide by 3.6, that is 27.8 meter per second. Acceleration is negative 6.5 meter per second squared and x equal to 20 meter. What do we need? What is the velocity of the truck at the end of this distance? Well, which of the equations will you use here? If you look at this, we are looking for the final velocity, isn't it? What is the velocity at the end of this? We have initial velocity we have acceleration, we have the displacement. Which equation contains all these? Initial velocity, final velocity, acceleration, displacement. In other words, the equation that does not contain time is the third equation. Vf squared equal to V0 squared plus 2ax. Well, we need to find the Vf. We know V0, we know A, we know x. So use all those values. That will be 27.8 squared plus 2 times acceleration is negative 6.5 meter per second squared. A times x is 20. There is an additional 6.5. You need to cancel that. There is only one 6.5 there. So V0 squared plus 2ax. Alright? So cancel that 6.5. And that will be 512.8 meter per second squared, because this is the square of Vf. Vf therefore is the square root of that, which is 22.6 meter per second. And B, what is the time taken to travel this distance? Well, this time we are looking for time. Well, we have now all the other quantities, so any of the equations would be enough. You can find the time taken. Tell me which equation is appropriate for that. You can actually use the first equation. That's the simplest equation. Vf equal to V0 plus AT. We have obtained the Vf, we know V0, we know A, therefore we can find the time. So 22.6 equal to 27.8 plus A is negative 6.5 times T, and you can solve that equation. That will be 6.5T equal to 5.2, or T equal to 0.8 seconds. You see, you can see the method of solving problems. What I'm going to do is, I'm going to stop this part here, and I'm going to continue solving more problems in the next part of this lesson. All right?